Okay, so we're going to look at a little CO2 marking system. These have gotten to be very popular because of the sort of the new technology and being able to build low power CO2s that we put in small marking systems, and these things are even commercially available for in-home use. So we see a lot of these, not just for marking, but these little systems also are for cutting also, and doing lightweight cutting operations, mainly non-metals. Okay, so where the Q-switched YAG and Q-switched fiber lasers are really better equipped for doing marking on metals because of the high peak power pulses. CO2s are really excellent for marking non-metals particularly. So let's get started talking about this. Our wavelengths, we're using micron, 10.6 micron is our wavelength. We're looking at continuous wave. We have an average power of 20 watts. We're using the ANSI default for an accidental or unintentional exposure for 10 seconds. 1 over E squared circular Gaussian. We have a beam diameter at waist of 4 millimeters, a beam divergence at 3.5 milliradians. That gives us an OD at observer range, at where our observer range is a half a meter, at 3.177. Worst case is 3.318. The difference being, let's see, we have a 4 millimeter beam diameter trying to go through a 3.5 millimeter limiting aperture, and we can see that we get about 72% of the power through the limiting aperture. So that's the difference we're seeing here between the OD at observer range and the worst case OD. Let's take a look at our ocular MPE is 100 milliwatts per square centimeter. The skin MPE is the same. As we've previously discussed, this is about water absorption. So your cornea and your skin starts absorbing right at the surface because of water. So the skin MPE is going to be the same as the ocular MPE, 100 milliwatts per square centimeter, times skin MPE. Wow, that's that's 1,500 times. The irradiance of the laser is 1,500 times what the skin MPE is. Let's take a look at the average power irradiance here. The average power irradiance is 150 watts per square centimeter. Our MPE is 100 milliwatts per square centimeter, so we can see, that's a really high. That makes sense. The time skin MPE would be 1,500 times. Something I may want to point out is, remember that the irradiance of the laser is about the power passing through the limiting aperture, and then we divide that power by the area of the limiting aperture. So this comes from the area of this limiting aperture, and you can see that it's only 0.096 square centimeters. Remember that we've maybe used to looking at the area of the limiting aperture for the eye, which that diameter is 7 millimeters, which gives us an area of 0.385 square centimeters. So you can see this really drives the irradiance up, this using this area, okay? And if we wanted to know exactly how much power is passing through the limiting aperture, we can click here and we can see that we have about 14.5 watts passing through that limiting aperture. Okay? All right. So let's take a look at our diffuse reflection. Worst case, 100% spectral reflectivity. The beam on target is small. It doesn't mean that we're trying to do a point source, because it doesn't matter. We're outside the retinal hazard region, so there's no such thing as point source or extended source. We're just keeping it small because it doesn't make a difference, so we don't need to change it. Observer range is 1/4 of a meter. Exposure duration is 600 seconds. The ocular MPE for the diffuse reflection and the skin MPE are the same, as they are the same for intrabeam versus diffuse reflection. Okay, because 10 seconds to 600 seconds, we get the same MPE. The NHC is about 8 centimeters, not much of a diffuse hazard there. We wouldn't worry about that. OD at observer range is 0. And of course, there's no skin hazard from the diffuse reflection for this particular unit. We do have the lens on laser. We have a 127 millimeter focal length lens. That's about a 5-inch focal length lens. The beam diameter we'll be using is the same as what we're using for the beam waist and the intrabeam, 4 millimeters. The observer range is 1/4 of a meter. The OD at observer range is about 2.8, and the lens on laser NOHD is about 6.8 meters. Okay, let's take a look at what if we used wanted a barrier, and we'll say the barrier is 1.5 meters away. We'll do it for both the intrabeam and the lens on laser. And we need to switch this to, let's look at the 1/E irradiance, and we can see that for the intrabeam we'd need a barrier that could withstand at 1.5 meters 117 watts per square centimeter. Now that might kick us up to a barrier that we needed a higher rating for. Let's say we were talking to our vendor and the vendor said, well, look, we have a barrier that is rated at 100 watts per square centimeter and it costs this much, and then we have a barrier rated at 250 watts per square centimeter and it costs a little bit more. It's at this cost. What I could do, now for the lens on laser, before I get to lens on laser, is only 2 watts per square centimeter, and that's because this beam is coming out of that focal point and has a much higher divergence. So of course 1.5 meters away we're not going to see that high of a radiance as for the intrabeam. But if we were worried about the intrabeam, what we could do is say, well, to save us a little money, what happens if I push this barrier back? We set it at 2 meters away. Oh, look at that. It drops down to 78 watts per square centimeter, where a 100 watt per square centimeter barrier would work. So instead of paying extra money, I'll just push the barrier back a little bit. Okay? So, yeah, that takes care of if we wanted to order a barrier where that would be. I think that's about all we want to talk about here. So that's about it.